Hello, I'm going to review everything for Chapter 8 for sequences and series. So I'm going to start with these first two examples where we're going to determine if each sequence is arithmetic or geometric, and then we're going to identify the common difference or ratio, depending if it is arithmetic or geometric, and we'll identify what the next term is by using that common difference or ratio. So the first thing I'm going to do is kind of get an idea for what's going on in these patterns. The numbers here look like they're growing pretty fast, so that tells me it's probably not going to be arithmetic. So I'm going to check if it's geometric by taking my second term divided by my first. 12 divided by 4 is 3. And then take the third term divided by the second term, which is also 3. And then I'll do it one more time just to show you that my common ratio in this case is going to be 3. It looks like I'm multiplying by 3 every time. So that tells us that if we were dividing going backwards, we're going to multiply going forwards. So my common ratio is 3 of this geometric sequence. Again, this is a sequence and not a series because we're separating these terms with commas. So it's a geometric sequence. 108 is my fourth term. If I want to calculate my next term, we would multiply by the common ratio. So you just need to take 108 and multiply it by the common ratio of 3, which means our next term would be 324. So for the second example, this one does not look like we're multiplying in this case. So let's check for arithmetic, which means I would take my second term minus my first. Negative 2 minus 5 is negative 7. And then negative 9 minus negative 2 is also negative 7. And negative 16 minus negative 9 is also negative 7. So this is going to be an arithmetic sequence. And my common difference in this case, D, is going to be negative 7. So if I want to figure out what my next term is, we're going to take negative 16 and we are going to add the common difference, which is negative 7, and end up with my fifth term of this sequence being negative 23. So two short little sweet problems just to get the idea of arithmetic or geometric and to calculate those terms. For these ones, we're going to evaluate each of these finite series using a sum formula. So we'll have to decide if they are arithmetic or geometric, and if it's arithmetic, we're going to use Gauss's formula. If it's geometric, we're going to use the formula that we have for a finite geometric series. So in this first one, take a second, kind of study this. I know what's going on. I want you guys to figure out what's going on. So take a sec. Hopefully you're thinking arithmetic. Looks like I'm adding 6 every time. So I'm going to use Gauss's formula, which says the sum of n number of terms. You're going to take the number of terms divided by 2, and you're going to take my first term plus my last term. So in this case, there is no ellipsis at the end, the little dot, which means this is a finite series, which is what the directions also say. So what we really need to identify is the number of terms. We need to identify the first term, and we need to identify the last term. So in this case, my number of terms, 1, 2, 3, 4, 5, 6, we have 7 terms. My first term is 44, and my last term is 80. So you don't even need to identify the common difference. You don't have to write an explicit formula for this. We are just going to use this formula right here. So I'm going to use 7 over 2 times the quantity of 44 plus 80. So you would want to do what's in the parentheses. First, I will simplify this fraction outside. 7 divided by 2 is 3.5. And then on the inside, 44 plus 80 is 124. So now I'm going to multiply that amount by 3.5, and I will end up with a sum of 434. So if you really wanted to go back and check your answer, the directions told us to evaluate this using a sum formula, but if you really wanted to go back and check, it wouldn't take that long. Just add up all these 7 numbers, and you would end up with 434. In the next example, this one is going to be a geometric. Take a look, see what's going on. I have a bunch of negative numbers, which if you're going to add up a bunch of these negative numbers, you're going to end up with a negative sum. So that's kind of a little check right now that we're on the right track, because if you end up with a negative answer, that's actually a good thing. So I have a geometric series in this case. It's finite again because there's no little dot at the end. It looks like I have 5 terms in this series. So I'm going to use the formula that says I'm going to take my last term, SM. So I'm going to take Gn times my common ratio and subtract my first term all over the common ratio minus 1. So in this case, we need to identify a few things from this formula. We need our last term, I need my first term, and I do need my common ratio. So in order to get that common ratio, it looks like it could be obvious. Again, you could take second divided by first, and you would get a common ratio of 2. I'm actually going to change color to do this. We're going to get a common ratio of 2. My first term is -3, and my last term is -48. So in this case, since there are a lot of negative numbers, we're going to be really careful with our signs. Just substitute all the values in as you see them. So Gn, my last term, is -48. Multiply that by your common ratio. I'm subtracting my first term, which is -3. And I'm putting all of that over my common ratio minus 1. So -48 times 2 is -96. Minus -3 means I really have a plus 3. And all of that jazz is over 2 minus 1, which is 1. So that is going to simplify to -96 plus 3, which is -93. So that would be your final answer. Again, if you were just to take all of these 5 terms and add them up, this is what you would end up with. So as far as a couple similarities between these, we needed our first and last terms for each of these sum formulas. The one on the left here with the arithmetic sum, using this formula, we needed the number of terms. And the one on the right, we didn't use the number of terms, but instead we found the common ratio. Next ones. So now we're going to move into sigma notation. Both of these are going to be geometric series. The finite geometric series, notice at the very tippy top of this, I do not have the infinity sign. So that means that these are the same thing. We have a finite series in each of these cases. And we're going to use that same formula that we did in the last one, except since the series isn't laid out for us, we will need to substitute some values in and calculate. So this formula, just to kind of go through this process again, this formula right here is your explicit formula for a geometric sequence. This top value here is going to represent what we call the upper bound. So if you substitute that value in for I in this case, what's going to happen is it'll calculate your last term of that series. And then the first term here, we're going to substitute the value of 1 in for I. And that's going to give us our first term. It's going to come out to 15, which is always your G1. And the 1.5 is going to represent our common ratio, R, because it is your base number here. So I'm just going to substitute a couple of these values in then, the lower bound and then the upper bound. And again, in order just to kind of backtrack a little bit, in order to use the geometric series formula, we're going to need the first term, the last term, and the common ratio. So I need G1, I need Gn, the last term, and I need my common ratio. So I'll start filling some of this information in. My common ratio is the 1.5. I know that my first term is going to be the 15. If you don't believe me, just substitute a value of 1 in for I. You'll get 1 minus 1, which is 0. Anything to the 0 power is 1, and you take that whole chunk and multiply it by 15, you're going to get a first term of 15. If you want to find your upper bound, I'm going to take 5 and substitute it in for I, so I'm really going to get 5 minus 1. So I'm going to take 1.5 to the power of 5 minus 1, which is 4, and I'm going to multiply this by 15. And I get a really big number, 75.9375. So now that I have all this information, I can use my sum formula. So Sn equals, I'm going to write out the formula again. You're going to take your last term times your common ratio minus your first term, all over the common ratio minus 1. So I'm going to take 75.9375, multiply it by the common ratio, 1.5, subtract my first term, which was 15, and all of that stuff is going over r minus 1, so 1.5 minus 1. So I'm going to slowly work my way at this. I'm going to take this last term and multiply it by 1.5, and I get a decimal that says 113.90, blah, 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 blah. It's going to be a huge decimal. I'm going to subtract 15 right away from that. So I'm going to write that value all the way here at the top. And then at the bottom, I have 1.5 minus 1, which is just 0.5. So then at the very end of this, I'm going to be dividing by 0.5, and I end up with a sum of 197.8125. So again, what that means, or I should say, how this problem is different from our last one is we can't just add up the 5 terms. We don't even know our 5 terms. We just calculated the first term and the last term, and we used the common ratio to evaluate this sum. Whereas in the last example, I gave you all the terms, so realistically, we could have just added all of them up. Number 5 is going to be a little bit different. A couple of reasons. First of all, I'm starting with a value of 0 down here, and we're going up to 6, which technically, if you count from 0 through 6, including 0 and 6, that's a total of 7 terms. My first term is going to be this value out front. Again, we're going to be substituting some information in. So I'm going to do first is just erase a bunch of this stuff down here that we just solved, just to make some room. So we're going to use the same information though, same formula. We're going to calculate some of these values. We will need our first term, we'll need the last term, and we'll need the common ratio. So again, just to really recap this is sigma notation for a geometric series. It's finite because we have an upper bound here that is not infinity. And again, it's geometric because this is an exponential equation. The variable is in the exponent spot, so that's just kind of your indicator that it's not arithmetic. So in order to figure out our first term, I'm going to substitute 0 in for I. 0.75, again, anything to the 0 power is 1, but we have to multiply it by this value out front, which is 50. So that tells me, again, I want to change color. Crap. That tells me my first term is going to be 50. The last term, I'm going to substitute 6 in for I, so I'm going to take 0.75 to the 6th power, which is a really ugly decimal, and I'm going to multiply that by 50 then when I'm done with that, and that's going to give me roughly 8.899. And then I'll take my common ratio, which is the base number, so 0.75. So these numbers, if you think about it, we're starting at 50, and we're getting smaller. We are multiplying by a number that's less than 1. So these numbers are getting smaller and smaller and smaller. So 6 terms later, or 7 terms later, we're left with a value that's almost 9, and we started with 50. So now we're going to take a sum, which I'm going to use that sum formula again. S of n equals, we're going to take our last term, 8.899. We're going to multiply it by the common ratio, subtract my first term, and then all of that stuff is going to go over your common ratio minus 1. So hopefully you have a calculator handy. Try substituting some of these values in. I'm going to take 8.899, multiply it by 0.75, and then I'm going to subtract 50, and I get a numerator of negative 43.32575. All of that is going to go over 0.75 minus 1, which is negative 0.25. So at the very end of this, I'm going to take negative 43.32575 and divide by negative 0.25. And I end up with a sum of 173.303. So in this case, we're starting with a value of 50. And you're adding a number to that is basically 75% the size because the 0.75. So you're adding a number that's going to be smaller than 50, and then you're adding a number smaller than that, and then after that, and then after that, until our last term would have been the 8.899. And if you would have added all those terms together, which we didn't even calculate the terms, but if you would have calculated them and added them together, you would get 173.303. Next ones. So with these, we're going to determine if each of these series is convergent or divergent. So notice we're in sigma notation on both of these with an infinity at the top, which tells us that these are infinite geometric series. So in this first one, we have a first term of 3, a common ratio of 0.25, and we're going to be starting from a value of 1 and going all the way to infinity. So the part with convergent or divergent, I'll make a little note at the top. If your common ratio is greater than 1, it means that the numbers are going to keep growing larger and larger and larger, meaning they're going to move away from 0. So that would be divergent. If your common ratio, assuming that it's positive and assuming that it's not 1, if it is less than 1, which means like 0.9, or if I say 4 over 10, or some kind of number that is less than 1, it would be convergent, which means that it is going to have a sum which we'll be able to calculate. So in this case, your r is 0.25, so since r equals 0.25, this is going to be convergent, and we are going to be able to calculate a sum. The sum formula, we're going to take our first term in this series over 1 minus r. And I love these formulas, they're very short and sweet. You only need 2 pieces of information to work this formula. You need your first term, which again is out front. You don't even have to calculate it. The 3 is right there. It represents your first term. over 1 minus 0.25. So whichever way you'd like to do this, if you want to go to the calculator, if you want to do it in a style of fractions, you're going to end up with 3 over 0.75. And that's going to end up, whenever you divide that out, you're going to end up with a sum of 4. All right, so our first term was 3, and we're adding to it a bunch of numbers that are smaller than it, significantly smaller than 3. And they just keep getting smaller and smaller and smaller and smaller and smaller. And the more terms you have as you keep going until infinity, eventually you're just going to end up with a sum, and that sum is going to be 4. Number 7, I really love. It's a very small amount of work, and that's because your R value is 5 over 4, which if you take 5 divided by 4 in your calculator, it's the best news ever. It comes out to a number that is greater than 1, and if it's greater than 1, it's divergent. I'm getting really excited because our sum is infinity. Blah, blah, blah. Okay, the sum is infinity. I got all pumped about that because we don't even have to use a formula. It just tells us that if your common ratio is a number that is greater than 1, automatically your series, it means the numbers are just going to get larger and larger and larger and larger and larger. And if you keep adding up all these numbers that are getting larger and larger, it's just going to be infinity. Love it. Okay, story problem time. Time to hate me. So, Terrence just won the Jumbo Mega Bucks lottery. He must decide between 2 payout options. For option A, he would be paid $50,000 for the first year, $55,000 for the second year, $60,000 for the third year, blah, 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 for a total of 20 years. For option B, he would get $50,000 the first year, and then every year after that, he's getting 6% more than the amount he was paid for the previous year. So the first one, it looks like they're adding the same amount every time. Looks like he's getting $5,000 every time. And the second one is a percentage. He's getting 6% of 50,000, and then you're adding that on. And then 6% of that larger number and adding on a larger sum. And then you're getting 6% of that larger number. So that one's going to keep growing exponentially, which tells us that the first option is going to be arithmetic because we are adding the same amount every time. And the second one will be geometric because you're multiplying by some amount every time. So since we're multiplying for that second option and it's growing exponentially, that will indicate that it's a geometric series. So it says which option will pay more in the 20th year. So that means what we're going to be doing is calculating A20 for the first one. And for the second one, we'll be calculating G20. So what we're going to be doing for this part A here is writing the explicit formula for each and evaluating it for a value of 20. So for the arithmetic explicit formula, AN, where n is any number of terms, you're going to take your first term plus the common difference times the term minus 1. So AN equals, we're going to take our first term, which would be the 50,000. Plus his common difference, which it looks like, again, he was adding $5,000 every year, and then n minus 1. So what we're going to be doing is evaluating the 20th term, figure out how much he gets after 20 years. That sounds like an awesome time. Okay, so you'd be putting 20, substituting 20 in for n. So if you do 20 minus 1, you're really multiplying by 19. So every year he's getting, so for 19 more years after, he's getting $5,000. So he's going to end up with $50,000 for that first year. And then after that, he's going to earn $95,000 more dollars. So after you add these two together, you're going to end up with a total of $145,000. So just in his 20th year, he gets $145,000. That isn't even the total. That's just in the 20th year. So you would add the year before that and the year before that. And if you wanted to calculate this series, which we're about to, we're going to end up using this value to total our sum. In the other side of this, so the geometric one, we're going to calculate, or we're going to write the explicit formula for a geometric sequence first. So g of n equals, you take g1, it's very similar to this. Instead of taking a1, we're using g1, and instead of adding the common difference, we multiply by the common ratio. And since this one is linear, you have the n minus 1 right next to the common difference. This one's exponential, so it will be in the exponent spot of your common ratio. So very similar formulas. I'm going to substitute in some values now. So gn equals, we're going to take our first amount, which is 50,000. I'm going to multiply by my common ratio. So he's raising 6%. So every year, he gets 100% of his money plus this 6%. So if he's getting 106% as a decimal, that comes out to 1.06, and that would be his base number. So that's the common ratio raised to the n minus 1 power. Now what I want to do is evaluate g of 20. So I'm going to take $50,000 times 1.06 to the 20 minus 1, which is 19. And in this case, I'm just going to throw all of this information in my calculator. It will do the order of operations for you. 50,000 times 1.06 raised to the 19th. And I end up with, in the 20th year, he's getting $151,279. And I'll even throw on the change, 98 cents. So he's almost getting that 151,280, but not quite. He needs 2 more pennies. Okay, so that's your last term of that one. I'm going to take those down on a sheet of paper because I have the feeling that we are going to be using those in a second. Blah, blah, blah. 145,000. The other one's 151,279.98. Okay. Next part of this problem, then, we're going to figure out which option is going to pay him more over the 20-year period. So in this case, we're going to be evaluating a couple of sums. So the first sum that I'm going to evaluate, I'll do the one on the left, which was arithmetic. So we're going to use the formula that says S sub n equals n over 2. You take your first term plus your last term. This is going to be a piece of cake because we already have our information. I know that my number of terms is the 20 years that he's been earning money. The first year, or the first term in this case, would have been the amount that they started him with, which was $50,000. And we just calculated the 20th term, which was $145,000. So all that we have to do then is substitute all of these 3 values into this equation. So S sub n, representing the total amount that he earned, equals 20 over 2. You're going to multiply the quantity of 50,000 plus what he earned in the last year, which was 145,000. So 20 divided by 2 is going to give me 10. I'm going to multiply that by 50,000 plus 145,000. That whole number on the inside is 195,000. So really what you're going to be doing is just sliding that decimal over one spot. So he ends up earning $1,950,000. That is a crap ton of money. Okay, so that's how much he earns over that 20-year span. This is an arithmetic series. It is finite. We're evaluating over that 20-year period. Now on to the geometric one. So S sub n equals, we're going to take our last term, which we calculated that 20th year, times our common ratio, which was the percentage that he was earning every year, minus the first term over r minus 1. So in this case, we need to know the last term, which we calculated out to 151,279.98, and that was the amount again that he earned in his 20th year. Our first term was that same amount that he started with as before, the $50,000, and our common ratio in this case was 1.06 because he was getting 6% more every year. So I'm going to take that information and substitute it into the formula at the top. So S sub n equals, take the 151,279.98 times my common ratio minus my first term. I'm just so pumped to see this total. I don't know if it's going to be more. I don't know if it's going to be less. My guess is it's going to be more. No, I'm just running on sentences. Okay. And I'm going to throw a bunch of this in my calculator. First, I'm going to do the 151,279.98, and I'm going to multiply that by 1.06, and I get 160,000, blah, 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 blah. I'm going to subtract 50,000 right away. So I'm going to get 110,356.78, and I'm going to take that over 1.06 minus 1, which is just 0.06. This is going to come out to a huge number. And it comes out to 1,839,279.65. So when it comes time to comparing these two models, I was wrong. I actually thought this one would be more. It looks like he gets almost 1.95 million from the one on the left and 1.84 million almost for the one on the right. So the first option, where he's earning the $5,000 more every year, is going to end up being more worth more in the long run, even though by that 20th year, it looks like in the 20th year, the geometric one paid more. It paid almost $6,000 more than the arithmetic one. But overall, when you add them up, the arithmetic ended up paying more.